Hello, and welcome to the second in a series of Blasch Precision Ceramics product information seminar presentations. Uh, I'd like to discuss the Blasch VectorWall reaction furnace mixing checker wall today. And I'm going to do this a little differently. I'm going to back up and discuss first a little bit of philosophy on refractory design, realizing that many of you may not be refractory engineers or process engineers for the particular units that we're discussing. So you have a little bit of overview on the design process, what we're trying to achieve, and how to offer more value. Let's start at the beginning. For example, in the case of old Greek architecture, engineers have been asking tough questions for thousands of years, like, how do we design this thing so the stone beams won't crack and fall on our heads, thus killing us? In this case, you can see they simply added more columns. This is referred to as the brute force approach, and while it is effective, it does have significant limitations in that you're reaching a point of diminishing returns and you remain limited by the parameters of the original design. The right question should not be how to make the existing design work better, but how to best achieve the aims that the existing system was designed to address. For example, how can we span greater lengths and support more weight? The right answer almost always starts with a fresh look at the problem in a blank sheet of paper, and it can sometimes yield solutions that are great leaps forward. The problem in the process industry is that things have been done a certain way for many, many years, oftentimes because of limitations in refractory technology. You're limited to relatively simple cast shapes or brick and mortar or castable refractory, and there are only so many things you can do with those. So the process has evolved in limitations imposed on it by those materials. So you want to get the process engineers and ask them, what is it that you are trying to achieve here? Not what is it that you're using today, how would you improve that, but what is that thing that you are attempting to do most effectively? And then when they can explain the process to you that way, you basically then build refractory around it in a way that enables them to operate in a most efficient manner. And sometimes doing that makes all the difference in the world. First, we're going to discuss mechanical reliability. This is because oftentimes these problems come to us cloaked in terms of reliability, longevity, and we need to address those, but then also learn to dig a little deeper. These photos that you're looking at are different structures that exist in combustion chambers, and they show typical shapes that are available to put in these systems. The lower left-hand photo is a series of bricks mortared together in an open weave pattern. The top center are stacking blocks. Bottom center is a baffle wall. A variety of different construction techniques, none of which are particularly reliable. Part of the problem with this is related to the strength of the mortar. Mortar in and of itself is not particularly strong bonding mechanism, and at high temperatures can only exhibit strengths of maybe 500-600 pounds per square inch shear strength, whereas the refractory material you're trying to adhere together will have 10 times that strength. So what we at Blasch try to do is to use the shapes themselves to hold or mechanically engage the pieces together, not simply cementing them and counting on the strength of the mortar. The other problem with the mortar approach is these units cycle repeatedly to very high temperatures, and this cycling, this expansion, this contraction causes the mortar to crack, to the slip plane to come apart, and the bodies then become relatively unstable, quite unstable. So we're looking to design with the strength of the material being the thing that holds the components together. In this photo, you can see a series of hex wall blocks in the beginning of the construction process. We were approached by a number of different clients over the years and asked to create a more stable structure. And what we did was to create a series of interlocking shapes. These hexagonal pieces nest very efficiently together, and the tabs and slots on them keep them from moving laterally against each other. So they become very, very stable just by virtue of the configuration. This particular installation is going into a groove in the hot face brick. There are really two ways to install these. It's the preference of the operator and the preference of the refractory installers, but the wall may be constructed into a groove that is created in the hot face brick by removing a couple rows of brick. If it is not desired to intrude on the integrity of the lining, you can build the wall on the hot face and then use a row of bricks on either side to contain it from moving back and forth. It's not going to move much back and forth anyway because of the way the pieces are locked together, but in this industry, usually it's belts and suspenders. So you'll see either the wall constructed between this ring of bricks on the right or into the lining as you see on the left. In this case, this is a wall in a large acid plant in Russia. They have, again, chosen to install this into a groove in the hot face brick. And you can see that in the bottom, there are some partial bricks. There is a fair amount of work needed to get started so that you're level and plumb, and you have good support for the blocks as they go up. So there's a bit of work required to get started, but once you get a certain along the way, as you see here, construction goes very, very quickly. And one thing to note is that in addition to going very quickly, the need for skilled trades, bricklayers, for example, is less than would be the case. In a unit of this size, to build a brick checker wall would require days and days of highly skilled bricklayers. And in this case, it's more like hours, and you don't need that level of expertise. So there's advantages there, both in timing and in cost. One thing to note here again is the openings are round. This is important because at high temperatures, you want to be in compression. If you look at the checker wall photos, you'll see the bricks are actually flat spans spanning open area. And when you have that situation, you have gravity pulling down on the middle of those bricks and they sag. Once they start to sag, they go into tension and they increase the rate of sagging to failure. So these are designed so that they're fully self-supporting. The openings are round, and in the bottom center you can see a manway, a removable manway, in case people need to get back and forth. The last step of the installation is the most important. and this wasn't obvious to us in the beginning when we were addressing the mechanical aspects only. But again, we were learning, and it took a few years to understand that the answer to the question, what is this wall supposed to do, is not that it should not fall down. That's not a process benefit. The answer is, how is this going to improve my yield? How is this going to make my plant work more effectively? And ultimately, we did learn to use these so-called vector tiles, these domes that are placed cemented into the exit end of the blocks and used to turn the gas 90 degrees as it comes through the wall, creating a big rotation. So that's the last and most important step. And again, this evolution from mechanical reliability to process improvement took several years the first time, and now we've gotten to the point where we can ask these questions much more early in the process, and benefits everyone more. So process. All right, these units that these vector walls have been going in for years are generally referred to as reaction furnaces or thermal reactors, perhaps thermal oxidizers or incinerators. It relates to combustion of gases. And what drives efficiency of the combustion process is to get the products of combustion together as quickly and efficiently as possible, mixed and together for the right period of time. Combustion is actually a chemical process, a chemical reaction, an oxidation reaction. So you want to have it proceed the optimal amount of time in optimal fashion. And all of those desires are wrapped up in the expression time, temperature, and turbulence. Those are the three things that you need to pay attention to that will give you the most efficient chemical reaction possible. You need to get all the constituents together in close proximity to one another. They need to be at the proper temperature for the reaction to occur, and they need to be together for long enough for said reaction to complete. So when you think of these vessels, you think of these three things. Now, there are a lot of different licensors out there in the world, and they have over the years developed their own designs and processes for creating the most efficient chemical reaction possible, and they are widely different, surprisingly enough. Perhaps not surprising when you consider that these designs predate CFD modeling, for example, and the various licensors had only their experience, their gut feeling to go on as to design the internals that would create this optimal reaction time and space. There are also a number of different burner systems out there in the world, and they've been evolving, and that has impact on these structures as well. For example, more recently, a series of high-intensity mixing burners have become available in the industry. They tend to be, well, first, very expensive, north of $500,000 and perhaps $1 million. But they are, they create very strong mixing and rotation. They have a short flame length. They are attempting to create the ideal time, temperature, and turbulence right from the burner end. More conventional burners over the years, burners from like John Zink, Hamworthy, Zico, Calidus, Combustion Solutions, They're typically just a big burner in a tube, long flame length, relatively little mixing. So those type of systems have required these structures in the furnace to make up for the shortfalls of the burner. And every once in a while you run into a burner that's mounted not at the end of the furnace, but perpendicular to it, and that's an effort to create rotation as well. So again, three of the different structures that you'll see in these types of units, these thermal reactors, would be a checker wall, which is the top center. That's just a 50% open area wall that creates turbulence and mixing. In the center is something called a choke ring. That is a restriction in the diameter of the vessel, and that creates a certain amount of return flow back toward the burner, back mixing. That's a design that's quite popular with Jacobs, Comprimo, Worley Parson. And then the bottom represents a baffle system, which you typically see in sulfuric acid plants, where they'll have several of those to create high shear mixing. Now, the choke rings and the baffles are interesting because you're actually returning, well, even the checker wall, returning a percent of the gas back toward the burner. And that rejection of the flow does two things. It creates a percentage of the gas that's going to be in the furnace a lot longer, and it also speeds the velocity of the gas through the body. So the gas that gets through the opening gets through much faster. You're creating a venturi, you're compressing the flow, you're increasing the velocity. So you have a very broad span of time that any particular specific particle might be in the furnace. When we started doing this, we used the example of microwave popcorn. I know it's kind of silly, but if you get a bag of popcorn, you put it in the microwave, you hit the popcorn button, and 2.5 minutes later, the bell dings, and your expectation is that you're going to have a bag of completely popped, perfectly done popcorn. That's because it's all in the spot it needs to be in for the time it needs to be there, and that's a very narrow residence time distribution in a very efficient series of chemical reactions. You would not expect to have 1/3 of the popcorn burned to cinders and 1/3 completely unpopped. That would be unacceptable to anyone. But the way these reaction furnaces, these thermal reactors operate often is like a poorly designed microwave. So you're getting lots of variation in resistance. So back to the structures, what do they do? What do they have in common? They're trying to shape the flow. They're trying to create the optimal combination of time, temperature, and turbulence within these furnaces. This graph will show in blue a vector wall distribution. You'll note that the highest frequency of perfect residence time is dead center, and the distribution on either side of that is quite tight. The reason for that is because as the gas passes through the wall and begins to rotate, it creates something called a plug flow. So that type of rotation and flow causes the gas front, if you will, to move very consistently downstream. Everything that's in that rotation is traveling the same length. They are going the same distance to the exit. You get a relatively tight, narrow distribution of your residence time. The red is a choke ring type of configuration where you have a percent of the material exiting very quickly. That's the material that goes straight through the middle. It gets a little boost from the venturi, and it's out of the furnace well before there's time for it to mix, much less react. The little section to the right is gases that have been rejected by the choke ring and have come back toward the burner or back mixing. They're in the furnace for much longer than necessary. And then in the middle, you've got the range at which the more or less optimal residence time exists. So you can see that it's much broader, much more spread out, and further away from residence time. We talked about rotation and plug flow. That's what's occurring here. I'm going to show a little short video of a comparison we did between baffle furnace and a VectorWall. And this is where it first dawned on us that this residence time distribution was the problem. These baffle furnaces, which are typical of sulfuric acid plants, are great mixers, but they really increase the residence time distribution. They really force the designers to build much longer furnaces so that the material that exits that much more quickly still has a distance to travel to exit the furnace. So you're adding walls, you have lengthen the furnace, you add a wall, you lengthen the furnace. It's sort of a self-defeating experience, whereas the VectorWall, the plug flow is proceeding at about ideally about the rate you need it to proceed to just complete the reaction as it leaves the furnace. Now, there are really two ways to look at mixing in these furnaces, and that's in a simple one-component system versus a more complicated multi-component or multi-chemical compound system. In straightforward Klaus unit, and in most of our early applications were Klaus units. That's a sulfur recovery unit. These exist in the refineries and gas plants to remove the H2S, the hydrogen sulfide that's created when you're desulfurizing gas or crude oil. If you were not to do that, you'd have a problem with SO2 and SO3, acid rain, all that stuff. So the fossil fuel is hydrotreated. The hydrogen that's used to strip the sulfur out creates H2S, and H2S needs to be burned. It can be done in one stage, one large open vessel. These are homogeneous feeds. It's a relatively straightforward exercise. The combustion of sulfur is similar. In the sulfuric acid plant, you burn sulfur to make sulfuric acid, and you just need to make sure your furnace is. The cartoon version looks something like this. You get the wall as close to the burner as you can so that when the zone of the most active combustion is occurring, you're right there at the exit of that. So you're really shortening the furnace up to where that reaction, that initial combustion is occurring. And then the rest of the furnace is downstream. It's mixing, it's setting up this tight residence time. Relatively straightforward. Where you can really make some money is in the more complex configurations. For example, not all Klaus units burn just H2S. These days, more and more folks are removing nitrogen from their feed sources as well. And removing of nitrogen with hydrogen creates an ammonia-bearing gas. It's called sour water stripper off gas. And one of two things can be done with that. It can be combusted in its own dedicated incinerator, which is costly. It's another complete train, big capital expense. Or more commonly, it's dumped into the Klaus unit. The Klaus unit is seen as something of a garbage disposal, if you will. It's not a profit center per se for the refinery. It's a cost center, and as such, it doesn't get the respect that some of the other units get. But if it's not in operation, the refinery could well have to shut down because you can't generate H2S without getting rid of it. So it must operate. It must operate efficiently. It's not going to make a ton of profit for the refinery, so it makes it a tougher sell, but it's a good learning experience. It was for us to show how these guys can make some money out of this process. Again, in units with sour water stripper off gas, you have to be very careful. You have to combust that ammonia bearing gas at a certain minimum temperature for a minimum time, or it's not going to completely break down, and it's going to deposit as ammonia salts downstream on waste heat boiler tubes, on catalyst, and it's going to reduce the efficiency of the plant, and it's going to increase your pressure drop considerably. So you have to be very careful with the combustion of this material. The analogy on the sulfuric acid side would be spent acid regen furnaces, where the operators are injecting used sulfuric acid into the thermal reactor, and it's being combusted in a way that breaks it down into ultimately sulfur, again, in new sulfuric acid. But these steps in the process have very different requirements for conditions. This is a busy slide, but it's just a schematic that shows the combustion chamber. It's got a choke ring in the center that's dividing the environment into two halves. And the operators are injecting the sour water stripper gas and 1/3 of the acid gas into the burner end, where the injection normally occurs. But then they take the remaining 2/3 of the acid gas and inject it behind this restriction. And what they're trying to do is to ensure that the ammonia is going to be combusted at a higher temperature in the front of the furnace, because putting more H2S in tends to lower the temperature. So they're creating two very specific zones here. In spent acid regen, you'll see sulfuric acid come in through the burner, spent sulfuric acid, and then you'll see air or oxygen come in behind this restriction. They're creating a reducing environment immediately in the front, oxidizing in the rear. And in the case of sulfuric acid, we were able to reduce NOx by 75% because we're creating a much bigger temperature differential in the front and back of the furnace than you'll get from some of these other structures, and we can talk about that in a moment. We had some modeling done. We have a technical agreement with DuPont MECS, where sales of these VectorWalls into sulfuric acid plants go through DuPont. They have worldwide rights to that. And as part of their effort, they had reached out and gotten some modeling done at one of their partners in China. A lot of these walls in the spent acid regen side go into China because of the growth of the refining industry and alkylation and all that. So what you're looking at here is a choke ring configuration furnace. You've got the various constituents of gas coming in the end, and you've got the secondary injection point behind the choke ring. And these schematics or these visuals show you things like gas velocity, molar concentration of sulfur, of SO2, of H2S, and temperature. And these are real reaction kinetic modeling outputs. They are very expensive. There are thousands of reactions that are occurring simultaneously in these furnaces, and you're probably talking $100,000 worth of modeling for output like this, but this is about as good as it gets. And what this does show you in a choke ring type furnace is you've got this high velocity down the center, and that does some things. It discourages mixing with a secondary flow. And again, if you're relying on time, temperature, and turbulence to create homogeneous products, you're not getting the time, you're not getting the mixing. And you can see by the exits of these other shots that the concentration of what these different gases is very uneven across the exit plane. So this is showing you what we were saying, that you're setting up a very non-homogeneous reaction with a broad resonance. And you can see that here. To the left is the time for the material going straight down the furnace, and to the right is the time going down the periphery where it's being rejected by the choke ring. In a VectorWall type, you get much better mixing, much more consistent properties of compounds at the exit, and that's because it's being stopped, if you will. It's being mixed and it's being rotated, and that takes the secondary injection at that point and spins it up. It blends it into the flow quite quickly, and it's got the rest of that time to complete its reaction before it exits. And this would be the residence time distribution of this VectorWall furnace, very narrow, and if you do it right, centered right about the optimal residence time. There's some similar modeling that was performed by a company in the United States, again, sponsored by DuPont, but they're showing VectorWall furnace that was installed a few years ago in Taiwan, CPC, Taiwan, and choke ring. They had issues with emissions, unburned material. They had vibration, they had hot spots on the shell. And you can see, again, the velocities through the center of this choke ring increase, and it gives you a broader distance between those particles that go straight through and those that do not, whereas the VectorWall in the top, much more consistent. This is an important slide because this is showing you the destruction of ammonia, sour water stripper off gas. You need a certain amount of time at temperatures in excess of 1250 degrees C. In this particular model, you need at least a half a second. If you don't have the gas mixed in the furnace for more than half a second, it's going to exit unreacted, and you're going to have real problems with ammonia downstream. Here you can see the VectorWall gas doesn't exit until almost 1 second, and that's well in excess of time required at that temperature to get the job done. And these results from this plant at Taiwan. The red is zone 1. That is the near burner side. So you're looking at a temperature average of maybe 1350 C, give or take. When we put the VectorWall in and removed the choke ring, those temperatures on average increased about 100 degrees, 150 degrees, or thereabouts, to a temperature at which combustion of ammonia was much more efficient. And the green temperature is the downstream behind the wall temperature from the VectorWall to the waste heat boiler tube sheet, and you can see that temperature has gone down considerably. Why is that? Well, it's because these domes, these vector tiles that we're putting into the openings are blocking a good percentage of the direct line of sight. So you're not getting the radiant heat transfer through the wall the way you are with just an open hole. So we're almost always going to see higher temperatures on the burner side and considerably lower temperatures on the waste heat boiler tube sheet side. These two colors, the purple is straight acid gas, and the blue is acid gas with the sour water stripper off gas. That's the ammonia bearing gas. We were able to increase the amount of ammonia bearing gas the plant could process by 50%. Why is that? It's because, and you have to be careful not to put too much in there or you're going to damage your equipment, but the temperatures are so much higher, the mixing is so much better that they were able not only to completely combust to eliminate the ammonia bearing gas, they were able to add 50% more of it and still get the job done, all the while increasing the capacity to combust hydrogen sulfide. That's because the volume of the furnace is being used more effectively. There are no dead spots. There's no material that's in there too long. It is the most efficient use of that volume. You get the stuff in there, you mix it, you react it, you get it out. So these folks saw increased capacity by 1/3 in acid gas and by 50% in ammonia. And then at the end of the day, the overall output of sulfur increased by 30% for that train. So there's an opportunity there to avoid the addition of a second or third train. If necessary, you can avoid having to put an ammonia specific incinerator in. This was a very good outcome all the way around. These are results from another company in which we've done, I believe, all of their tail gas incinerators now. Tessenderlo Curley is a company that contracts with refineries and gas plants to process their H2S for them, and then they use that to create sulfur-based fertilizers. But in the tail gas incinerator, interestingly, you are going to be using fuel gas to combust all the odds and ends that are left at that point. You know, in a sulfuric acid plant, in H2S combustion, those materials combust themselves. So you're not adding fuel once you've gotten the reaction started. In a tail gas incinerator, you're running on almost all fuel gas, and we were able to reduce the fuel gas requirements by almost half. That's real money. We've also, if this is attached directly to a stack, are able to decrease NOx greatly because, again, the temperature downstream of the wall is much, much lower and you're not creating thermal NOx. These guys had been adding excess oxygen to the vessel to try to drive the process to completion. They were able to stop that. They're saving costs in oxygen. They've eliminated hot spots on the vessels and no issues with vibrations. So very good results. And again, once they started putting these in their facilities, they converted all their facilities to this approach. Along the way, we've come up with, the more we learn, the more we understand other potential uses for. We are using the VectorWall to control flow, to control temperature distribution, front to back, hot to cold. We're using it to control the time that the material may be in the system. This is a piece of equipment called a CO boiler. And you'll find those in some FCC units where you're creating a fair amount of carbon monoxide and you're going to combust that. You're going to drive it to CO2 and then take that off. These units, some of them, depends on the licensor, are U-shaped, meaning the CO is coming in from the top right, it's mixing in the combustion chamber, the bottom right, and then it's expected to turn the corner and head back upward over a series of convective heat transfer surfaces. We got some inquiries from some folks that were saying, we're having problem with abrasion of catalyst fines are trained in here, so the refractory lining along the bottom and back walls is being abraded, and they're not getting the full effect of the convective heat transfer surface. So they wanted to know if we could use a VectorWall to attenuate the flow coming out of this combustion area. And this is a temperature profile as compared to the velocity one that was on the prior slide. This shows the heat remaining in the back wall along the location of the highest velocity flow, and that's where all the abrasion was. But then you don't have good coverage of your high heat across these tubes, so you're not collecting as much heat as you could or would if it were more spread out, is what you see on the right. So in the two cases that we put these in, we saw considerable improvement in not only the longevity, but also the process efficiency of the unit. And lastly, this is a thermal oxidizer in an investment casting aerospace company where they're melting wax out of investment molds. In that process, you take blades and vanes, airfoil shapes, you mold them into wax shapes, you put them on a tree, if you will, and you take that tree full of parts and you repeatedly dip it in a ceramic slurry to build up a big shell. You then melt the wax out of that shell and pour metal in, and that's your investment casting. The melting out of that wax creates volatile organic compounds, VOCs, and the purpose of the thermal oxidizer is to destroy those. And again, along with the chemical industry, you want to make sure that they're in there long enough to be destroyed, that they're properly mixing so that they can properly react. And this wall here looks closed. It's actually not. These domes are a little bit different shape. They still allow flow through the wall, but they stop almost all radiant heat transfer. So this is a very efficient use of the VectorWall concept. So once again, to recap, always ask, what are they trying to achieve? What is the customer looking to do? If they lived in a perfect world and could design the process from scratch, what would it look like? Then you can start to put refractory around that, and perhaps you design a cathedral with arches instead of a square little church with tiny square windows, for example. Also, take this process and apply it to other applications where people may not be happy with the way things are. They've just always been that way. Ask questions. Ask them, how can we make things better? And we're stumbling across new uses for these products all the time. And you may too. Thanks.